And with that, I welcome Elster from NTNU as our first speaker. So, there you go.
Thank you. This is my honor to be here at the HPC conference at Rice on oil and gas. It's not my first time here, but I'm still happy that Jan Erik Ødegaard encouraged me to come. My husband and daughter are actually living in Austin this semester, so that was another excuse, right? Generally, I'm actually located in Trondheim, Norway. So, any professor from any university, I will claim, would not be doing much if it wasn't for their graduate students. I mean, that's the passion and why I am a professor, is to be able to educate the next generation and work with them. And so this talk, or any of the work that I am referring to from my group, would not be possible with any of the many graduate students that I've worked with through the years. And here's a picture of some of them. And here's a more recent picture of my research group. This is when we were celebrating my last PhD student graduating, who is now actually working for MathWorks in England, Cambridge, England, on their parallel tools. So you may actually see some fruits of his work in your daily work if you use MATLAB. And I think some of you have heard of MATLAB. And the rest of them are some of my recent master students and some previous students, and a visitor, Gavin Taylor, who I will talk more about later. So my lab back in Norway, not surprisingly, given the funding situation in Norway for HPC research, is related to health sciences, meaning medical stuff, and oil and gas. And you've heard of this company called Equinor or Statoil, I'm sure. So they have been, and I actually worked for Schlumberger in Austin, Texas, before going back to Norway in 2001. So I have some background from the oil and gas industry originally. I also collaborated with people at my university in everything from physics to process engineering, where we look at, I mentioned that's an energy project I had with a master's student, looking at how to orient the solar panels with the sun using ray tracing on GPUs. So that's related to energy. Maybe not oil, but certainly energy. And also, of course, the natural ones, collaborators in oil and gas, and medical with people in EE and applied mathematics. I'll give you a little bit of rundown of a history of AI and HPC, but from my perspective, what have I been involved in? Of course, here I'm kind of giving away my age, but I think that's okay. I'm not shy to be past 50. So I actually started in the 80s, where we actually programmed in concurrent and parallel Pascal. That was sort of my first introduction to using more than one core. Now, why would we want to use more than one core? Well, this is an HPC conference, so we kind of know that we've hit the power wall a long time ago. So we can't just rely on the processors getting faster. We need to actually use several cores, preferably thousands of them, to get what we need to do. Not because it's easy, because it's not easy to program thousands of cores, and a lot of people here will tell you that the ecosystem for that is very important, just like Arm mentioned in the previous talk. But this is how we started with, I started in parallel computing. At the same time, I took a graduate course in AI at the University of Massachusetts, where I was as an undergraduate, by Paul Cohen, where he actually covered all 600 pages of his AI handbook. It was a grueling final. I think we actually handed us a glass of champagne at the end because he was afraid we were going to murder him. And then in 1986, I spent my first summer job at Christian Michelsen in Bergen. They had the first Intel high-performance hypercube outside of US, and it was called the Intel IPSC, which is called Personal Supercomputer. Now, Nvidia likes this thing to state they got the first personal supercomputer, but Intel actually used this term back in 1986. And we all thought of it as, or commonly called it, the hypercube. At the same time, we also had it at Cornell, where I was a graduate student, and NTNU, although I wasn't there, got its first Cray. You'll see at the same time over in AI, there was this big project initiative over in Japan called the 5th Generation Computing Project, and Satoshi may mention it tomorrow, I don't know, but it was one of those things that kind of kick-started HPC and AI over there as well. Now then, in 1987, I spent a summer at Yorktown Heights at IBM's research facility there. And I swear that's the time I got to use the most percentage of the world's supercomputing power, because they had 4 IBM 3090s in-house at the time. We connected them together, and we did multitasking across the 4 IBMs at high priority. And since that was considered 4 supercomputers at the time, I don't think I'm ever going to get to connect 4 supercomputers and run at top priority again, but it was a lot of fun. Those machines were vector machines, and this is a theme you'll see reoccurring, because what you see in GPUs today is they really are like vector machines. A lot of the thoughts go, how you program and how you have to do things in, single instruction fashion, or single threads, as they like to say today. So you'll see some of these things, just like the oil industry. The HPC industry is cyclical, right? You see the ideas coming back. You talk to RISC processors are coming back, it's cyclical. Then in 1988 to 99, Intel came. There were some more, versions of the Hypercube, and then the BBN network that we had. It was sort of not quite a supercomputer, but at least an HPC computer. That I had a project with one of Keshav Bengali's students at Cornell. At the same time, this is where you saw AI revival, right? The big sort of last wave of AI where you talked about expert systems. Later, there was a wave of case-based reasoning systems. And now, we're, no doubt, just from this room here, a lot of people want to hear about AI. The latest AI, where you have actually focused more on optimization, right? Casting things into optimization problem. In 94, when I was finishing my PhD, I was very happy to use the Kendall Squirrel research machine. Probably a machine not a lot of you have heard of, but it was considered a very hot architecture at the time. It had a ring of rings, and we had access to a total of 1 gigabyte of RAM. And you kind of all can laugh, because you can look at your smartphone today, and you probably have more gigabytes on your smartphone, or at least your tablet. But that was considered a really cool supercomputer where you can actually simulate millions of particles, right? That means you can do that on your smartphone today, right? This is how it's been advancing. At the same time, you heard Robert Brooke, one of the co-founders of MIT AI Live, say elephants don't play chess. And there was a lot of emphasis back then in the bottom-up approach, the expert system approach in AI. At the same time, I was actually called in to interview thinking machines over in Boston, and was considering working for them since they had recruited me. Well, the week after my interview, they filed Chapter 11. And that's actually what made me go to Schlumberger in Austin, because I figured Schlumberger wouldn't go Chapter 11 on me the week after my interview. So that is my story, actually. So it also changed a lot and the HPC industry was not as hot for the next several years, as you may know. SGI System was another one. They did also call me for an interview, and they had also several reorganizations through the years. I also worked on some IBM SP system while associated with Schlumberger. I should also mention that I was part of the MPI Standards Committee, MPI 1 and MPI 2, both as part of Cornell and as part of Schlumberger. And in 1997, as far as what I knew about AI, I was fascinated by the fact that Kasparov, one of the top chess player, was beaten by IBM Deep Blue. I think a lot of us remember that. Then 2001, Thomas Sterling had this Buell cluster, and we all start hooking our computers together into big compute clusters. And I'll claim that any supercomputer today really is a bunch of computers hooked together over a network. Whether it's your fast proprietary switch, or if it's like InfiniBand or just the Ethernet, you still have to think about distributed computing as well as shared memory. At the same time, I have this actually running around, well, not that exact one, but running around my living room is your vacuum cleaner. I don't know if anybody will call it AI these days, but it's quite useful, right? But it's not quite as intelligent as we may have thought it to be. Then in 2006, I was the director of computational science and visualization at NTNU. We installed and look at the machine, an IBM supercomputer, but had 7+ teraflops. This is no more than you have on your Tesla Volta card today, right? So you see, again, things change rather rapidly. And this is what I like you to think about when you think about what we should do in the future and what possibilities are in the future. We also start looking at programming these GPUs. At the time, there was no good tools. There was close to metal on AMD, and where it could do some annotated C or CG. That was really looking like a graphics program, but we kind of cast our problems into a graphics program. But, and a lot of my colleagues were not a lot, but at least a couple of my colleagues were kind of laughing at me when I spent almost $1,000 on this gaming card for a master's student to program up a wavelet transform. Well, gee, healthcare really liked it and put it in the high-end ultrasound scanner. And as you know, most of ultrasound computers, ultrasound companies today use GPUs in one way or the other. And we got a 40 times speed up on our wavelet transformer. So that was a very big deal when you try to do things real time. And you see a lot of potential in the future to put ultrasound scanners even on sort of handheld devices that could be used in the field for the very reasons that our smartphones are becoming so powerful. I wasn't really working much on AI at the time. That's why I put it in parentheses. There were some interesting things being developed, certainly on the AI side. In 2008, we opened formerly my lab. There was a big supercomputer that was basically a big cluster up in Tromsø. And we also got started getting donations from Nvidia since they liked our work. At the same time, Apple introduced the iPhone with speech recognition, and using the thousands of powerful computers running parallel neural nets, learning how to spot patterns in them. And that's sort of the basis of what we do AI today. You try to spot data and spot patterns in large amounts of data. Now, if you then look, finally, the last few years, we got more donations from Nvidia. We used more GPUs for more scientific research. IBM actually won with their Watson machine Jeopardy. We got a new supercomputer, and we had a EU project that integrated cloud and HPC. So all these things led to, today, we just got into my research lab 2 nodes of what was known as Summit machine here in the US, which is the world's largest supercomputer. It has an IBM AC299 Power 9 architecture. We have 2 nodes of that at our lab. It's a very much smaller scale, but at least it allows us to do fun things. And at the same time, I'm the PI for the project that just got a DGX2 right before Christmas, which has 16 of the Volta GPUs, and we're looking to doing a lot of exciting work on those. So I mentioned only 7 teraflops was that whole machine room back in 2006. Now I can pretty much get it on the card. And when I was on the tutorial committee in 2007, somebody from Nvidia, David Lopke, wanted to give a tutorial, and some of my colleagues on the committee saying, "Oh no, that's just a commercial company. They're just doing, they're just going to be advertising. It's not real." I kind of had to convince them, and it was the most popular tutorial 3 years running. And as you can see, by 2010, as it's shown down there were GPUs on the top 500 list and supercomputers. And why do we care about GPUs? Well, you can now get 5,000 tensor or CUDA cores per card, 640 tensor cores and 5,120 CUDA cores in one card. And you'll notice that the double precision on this Volta card is 7 to 7.8 teraflops, right? In fact, the DGX2 is known as a 2 to petaflop compute box. It's only about yay by yay, right? More than 3U rack, but definitely more than half a rack. And today I have supervised over 40 master students within GPU computing and over 75 overall. And I'm actually looking for a couple of PhDs, so if you know anybody wanting to work in the interface between HPC, let me know. So how can we use the power of the GPUs and AI and combine it for better high-performance computing? And note that also AI have made a lot of leaps forward. They used to have to build the models, spend a lot of time on model building, but now that has a lot of it has been automated with machine learning, right? And Nvidia itself now markets itself as an AI company rather than a gaming or a graphics company. And you can see why they've added these tensor cores, this 4x4 matrix processing arrays that are optimized for deep learning. Now for us in HPC, now we have to scratch our heads and say, how can we use all those tensor cores for HPC? Now they're it was hard enough when graphics came around and was only a few, it was half precision. It was single precision. Now it's half precision. And we had Gavin Taylor coming and visit us for a year at a lab from the US Naval Academy. He's an AI expert, and he and his grad students were at our lab. And the girl is seeing that a picture. She was not something we'll say in Norway, but working on cyber warfare. We call it usually cyber security, but same 2 counts. If you look at the current projects, we have a new project with the physics department, down computational X-ray microscopy, and we're also integrating AI and HPC. Not everything in AI is successful. This we should write. We had to try to train a neural network in order to predict how compile optimizations could do. That was not as successful. It may not be because of the problem itself, but maybe the problems we chose, which was the CUDA SDK. We did have a project that was successful with physics, where we looked at the actual wave equation in 3D, and that worked well with GPUs, had a 10x speed up, and that's the project for which we also will be having an combined AI/HPC student look at, because we're both doing the HPC part of it, and also looking at these images coming off this microscope. We have also looked at unstructured data, but that's really a pure HPC problem with my previous students. But like I mentioned, we can also hide the memory hierarchy. Here it is, and I want to emphasize AI for HPC, not HPC for AI, right? How can you use AI in HPC as opposed to how can you provide HPC for AI, if you understand the difference. So here we're trying to use AI details for how to do performance portability. So we look at a bunch of different parameters like thread block size, thread coarsening, thread mapping, what kind of different memories, and then you try to speed up with this neural network. And that was actually quite successful. You have try to build this model, and then you presumably build a model, then it can predict what is the best optimization you can do. I'll skip this slide and we'll look at some of the results. So here you see, if you on some older machines, you can figure out the configurations looking differently. Now, because the problem is, if you have a code and want to move it from one computer to another, especially in the GPU world, we have a new GPU card coming out every 6 months with a different size of memory, shared memory, the different kind of memory configurations, you need some kind of automatic auto-tuning or some kind of optimization scheme that hopefully is not manual. And that's what this is all about. We also looked at the CUDA backend for the work, and also looking at, also, as you see, another interesting, more image side is the one, 3D external visualization of selected object, which could be like fish inside water. We do have a project, we're working with Equinor on the OPM project. That was supposed to be a poster here, but he actually, unfortunately, the grad student withdrew, so that project is now done by Netherlands, so you won't see the poster here, but you can certainly talk to me. Looking at AI news here towards the end, you'll notice that in 2018, in October, This Way Out was published by, among others, Devika Subramaniam here from Rice, talking about how hurricane evacuation routes and how your home here in Houston, if you live here in Houston, whether the risk for it to be flooded or not is present. So I look at Harvey, if you want to look for that, and I strongly encourage it. It's a very interesting paper. Like I said, it was published in Scientific American. They also, in February 10 this year, there was a big report on basic research needs for scientific machine learning. You can look at information more there. Has lots of interesting points for how you combine scientific computing and AI. Just came out last month. Finally, you should be cautious about this AI stuff. And if you don't think I'm the only one saying it, even your colleague here at Rice, Dr. Genevera Allen, and I've talked to Vicky, will tell you as well, you know, not all results are reproducible, not all results are predictable or trustworthy. Google can say they have a 90% success rate on something, and then you put it out in the field and it may fall down to 50%. That actually happened in one case. So you shouldn't think of this magic black box. It is a black box, but be aware you should be thinking about this thing when you move on. Finally, I want to thank everybody. We have a great fun field, well, very excited about everything happened, both in HPC and AI. Please come and talk to me or contact me at my email address. I'd love to talk to you some more. There's lots of stuff going on. And thank you very much for listening to me. And I just was selected to the IEEE Distinguished Visitor Program, so IEEE will pay me to go to your place if you have your section invite me. Thank you.